Welcome to the lecture for November 28th. Today we are going to be covering composite and inverse functions. The objectives for this lecture are to find and evaluate composite functions, determine whether a function is one-to-one, and define the inverse of a function. As you can see that this lecture is going to be corresponding to section 10.1 in the textbook. I recommend that you use your textbook to follow along with the homework as much as possible. So first we here have question number 1 from homework 22. We are given two functions, f of x and g of x, and we are to calculate f of g of 0 and g of f of 0. So let me walk you through that process. So in part A, f of g of 0 is taking the function g, evaluating it at the point 0, then taking the output of g of 0 and then plugging it into f. It's like a double evaluation. So first we want to figure out what is g of 0. So I'm going to copy this again, leave parentheses here, and now I'm going to replace g of 0 with what g of 0 is equal to. So if I were to come over here to the g function, I can see that g of 0 is equal to 6 minus 0 squared, which is 6. So this output of g of 0 now gets plugged in here. Why? Because g of 0 is equal to 6. And now I have to evaluate f of 6. So here's the f function. So we're going to just evaluate as we have in the past. I'm going to replace x in this f function with 6. And then I have 9 times 6 plus 5, so 54 plus 5, which is 59. So 59 is the answer to part A. That goes right in here. Next, for part B, I am evaluating g of f of 0, so I've rewritten it right here. So I'm just going to copy these g parts again, the g letter and the parentheses. And now I need to figure out what f of 0 is. So f of 0 is 9 times 0 plus 5, which is 5. So that means I am going to replace f of 0 with 5. And now I can evaluate the g function at 5. So that would be 6 minus 5 squared. 6 minus 25 is negative 19. Which then goes here. Okay, so now I'm going to clear all this. I'm going to select Show Answers so that we can see the answers as I go through. This one was 59 and negative 19. We already know that. But I want to have the answers up here so that we can continue to see what those answers will correspond to. Okay, now we're going to move on to some additional practice here in question number 2, and this is the same concept as we did in question 1, so you can walk through the exact same thing. It's just giving you a chance to practice the concept. You want to have repetition so you can understand this more thoroughly. There's a video to help you with that. Again, you're just going to be plugging in 4 first into the g function and then take the output of that and plug it into the f function. So I'm going to do one of these, but then the rest is just the same as we did before. Okay, so first we are going to find f of g of 4. To evaluate f of g of 4, we need to find out what g of 4 is equal to. So we take 4 and we plug it into the g function, as shown over here. And then this is 32 plus 12 plus 8, which is a total of 52. So then we replace g of 4 with 52. And next we plug in the number 52 into the f function. So that gives us 2 times 52 minus 4, which is going to be 104 minus 4, which is equal to 100. And that's what we expected our answer to be, because I am already displaying the answers. Okay, so next, if we scroll down, we'll see that number 3 looks exactly the same as the previous ones. What's different about this one is that we have a constant function. So then the g of x is equal to -3 is what makes this one a little tricky. So let me just explain how this works, and then you can continue on with working through it. Let me just do the first one so you can see it. We need to evaluate g of -9. Now, g of x is always going to have an output of -3. So whether you have g of 0, that's an output of -3, or g of 2, that's an output of -3, or g of 100, or g of pi, it doesn't matter what number you plug in. Sure, let's do pi. The output is always, with a constant function, going to be the same. And you can tell you have a constant function because on the right-hand side of the equation, you'll notice that there's no x, okay? There's just a number, there's no x. That's a constant function. So that means that the output of this is -3. And then once you figure out what this part is, now you do need to plug in -3 into this right-hand side. And so we have 6 times -3 plus 5 is equal to -13, just as we expected. Okay, so we've evaluated specific numbers, and now we're going to plug in variables. Here we have a new notation. So what is this crazy looking thing? This is f and then a little circle and then g of x. This notation we see on the left hand side is equal to this notation on the right hand side. So this is not specific to this problem. This is actually just a general thing for you to know that these whoops, that's not what I was trying to do. That these notations here are actually meaning the exact same thing. So we're going to take the f of x function, and we're now going to copy just like we did before. But this time, instead of replacing g of x with a number, we're not evaluating at any specific point. So we're going to take g of x and copy the entirety of g of x as it is. So that would be the 4x squared plus 5x. So what do we then do with this? Now we're going to plug in this entire binomial into the f function. So let me show you what that looks like. The function of f is 5 times something plus 4. So here I have 5 times something plus 4. What is that something? That something is this entire binomial. So we rewrite that in the blank here. And then we're going to use the distributive property and collect like terms, etc. In this case, we're going to end up with a trinomial. You can actually see the trinomial right here. It's 20x squared plus 25x plus 4. So that same thing would be written right here. Okay, so if you need further help, if you want to see an additional example, you can come over here to this video right here, and that will give you an additional example.
F of g of x. So remember what that
there's
means? You have to have
there's
this
a
little
second
circle. It's not a
example
dot.
available for
That
you.
means f of g of x. Okay, so that means f of, well, what's g of x? G of x is x plus 3.
So again, you can watch more of that if you would like. Alright, so now we're moving on. Question 5 is the exact same thing as we just did. It is function composition extra practice, so you just need to repeat the process. There's a couple videos for you. There's nothing new about these. Same thing with question number 6. One thing we're comparing here is f of g of x and g of f of x. And notice that f of g of x and g of f of x are not the same thing. You end up with completely different things. So this is not multiplication. Function composition is not commutative. Up here you'll be doing f of g of x, g of f of x, f of f of x, g of x. Remember that the notation here, f of g of x, is the same thing as this one. So let me just remind you again of notation in case that's confusing for you. That the notation that you see here is the exact same thing as what you see down here. F of g of x means this. And likewise, for this second one, g of f of x notationally means the same thing as this one right here. So that means that when you are working through number 6, you can refer back to these notations from number 5. And we are repeating the process again here for additional practice. Through repetition, you will start to get a hang of this, and hopefully it will start to flow. The more you do it, the more efficient you should get. We have several of these examples, and then we're moving on to a whole new topic. And what is this new topic? This new topic is, what does it mean for a function to be a one-to-one function? Okay, in order to, or rather determine whether a function, y is a function of x, is a one-to-one function, we're going to use what's called the horizontal line test. This should remind you a lot of the vertical line test. The vertical line test was whether we have a function in the first place. The horizontal line test now tells us whether we specifically have a one-to-one function, which is a special kind of function. And graphically, we can figure out whether or not we have a one-to-one function by using the horizontal line test. So the horizontal line test draws horizontal lines through a graph. So if we draw a horizontal line through a graph, if there's, hold on, let me try using an actual line. Okay, if you draw a horizontal line through a graph, we can do this for all of these graphs. We can see whether or not we have one-to-one, and then we also are going to want to check whether we have a function or not too, because that is part of it. So let's start with the one-to-one part, the horizontal line test. Right here we do in fact have a function that passes the vertical line test. But you'll notice that there is more than one location for this graph. If you draw a horizontal line through this graph and it hits more than one location, then this one is going to be failing the failing the horizontal line test. So that means we do not have a one-to-one function, so we do not want to check the box. However, over here you'll notice that when we draw horizontal lines through this graph, no matter how many different horizontal lines we draw, we're never having a point where the horizontal line intersects more than once. So this one then is a pass for the horizontal line test, so we do want to check this box. Now over here, we can see that it's going to fail the horizontal line test because it's hitting more than once, so this is another fail. But actually, this was problematic in the first place because if you try the vertical line test on this graph, it also fails. You can see more than one location where the graph is going to be intersecting, and so this one not only fails the horizontal line test, but it fails the vertical line test, which means that it's not even a function in the first place. Nor is this one right here. If we were to draw a vertical line through this is a review from earlier in the semester of the vertical line test. Even though this function passes the horizontal line test, because it fails the vertical line test, I can't keep this one either. I can't select this one because we have a fail. And so this one fails the vertical line test. And the requirement is that we have to have y as a function of x, and we have to check whether it's one-to-one. We've already learned earlier in the course how to check whether y is a function of x with the vertical line test. These ones passed that. But now we're learning the horizontal line test to check if it's one-to-one. And of all of these combinations, this one passed the vertical line test, so it was a function, but it failed the horizontal line test, so it was not one-to-one. This one passed the vertical line test, so it was a function, and it passed the horizontal line test, So this is both a function and one-to-one, so we check this box. This one failed both tests. It fails the horizontal and it fails the vertical, so it is neither a function nor one-to-one. In this one, it passes the horizontal line test but fails the vertical line test, so while it is one-to-one, it's not a function. So of these combinations, you have to pass both the vertical line test and the horizontal line test, or the graph does rather, in order for you to check the box. Okay, so let's try this with two more. We'll review these. Alright, let's start with the vertical line test. So if you were to draw a vertical line through this graph at any given point, you can see that no matter where you draw your vertical line, it's going to pass because there's only one place of intersection. So this one is a function, so yay, that's good. And next we want to see whether it's going to pass the horizontal line test. So as you can see, the horizontal line that we draw through the graph at any point, if we draw a horizontal line, no matter where we draw the horizontal line, we're going to end up with only one intersection point as well. Whether you draw here or anywhere along the graph, you're only going to get one intersection point per horizontal line. So that means that this one is another pass. It passes both the vertical and the horizontal line test. And this one over here, while it passes the vertical line test, every vertical line you draw through this graph will only intersect once, so this one is a function. However, it's going to fail the fail the horizontal line test, and that horizontal line test means that it's not one-to-one, even though it's a function. So you can see the fail because it hits more than one time. If that was a little confusing to you, I recommend that you look at 10.1 example 10.4, which is going to walk you through the same concept again. Perhaps the explanation in the textbook will be a little bit more clear, or else just practice this problem and then see which ones you're getting wrong and why, and refer back to this video. Okay, so now we're going to move on to question 9. We are looking at something new, and that is inverse notation. But before I teach you this new concept of inverse notation, I'm actually going to close out this video and start a whole new video for the next topic, because when I was filming my lecture for my trigonometry class, it took me over 5 hours of filming based off the number of glitches and errors I kept getting. So, in order to avoid that same scenario, I'm going to break this lecture into multiple smaller videos so that you can string them together and work through them as needed. Alright, so now proceed on to the next video and we'll pick up with question number 9.